So aloha and thanks for joining us. Good morning, afternoon, or evening, depending on where you are. Today, we give a webinar on the part one of our field study of discrete sample variability. And this, you see, I'd like to acknowledge first the co-authors on this study, myself, John Peard with our office, who got multi-increment sampling started here in Hawaii 10 years ago, Jordan Nakayama, and also Marvin Heskett with Element Environmental helped us out in the field. And down at the bottom is a quote from Albert Einstein that I want to reference real quick. If I had 1 hour to solve the problems of the world, I would spend 59 minutes on explaining the problem and 1 minute on explaining the answer. Well, that's what we're going to do today. We're only going to talk about the problem with discrete samples. We're not going to talk really any about incremental samples or multi-increment samples. We might do that a little bit in the second webinar. Quick acknowledgements. First, US EPA Region 9, the field study was funded under a grant, a state response program grant to Hawaii Department of Health from Region 9. And we use this grant to do small research projects every year. I also want to acknowledge the numerous consultants and regulators who provided input on the study and continue to be involved in the discussions. And mostly I want to acknowledge the skeptics who are forcing us to explain the limitations of discrete sampling and the need to transition to incremental sampling in more detail and make it usable in the field. I would include all of us, definitely myself, in the skeptics group. So we're constantly questioning what we're doing and why we need to change, and especially now what specific problem is. We really haven't done a good job of that in the past. We've done a good job, I think, of explaining how decision units and incremental sampling works, but we haven't done a good job of explaining the problems, and that was the basis of this field study. Quick references, the study, small-scale variability, discrete soil sample data. The last update was June 2015. And we're going to talk about part one today, field investigation. So we're just going to present the results. And in 2 weeks, we're going to talk about the implications for use in environmental investigations. The report is currently posted on our webpage. You see the address below under the What's New section. It's dated July 15th, notice to the What's New section. All the data are also posted in Excel format for anyone who wants to look at the data in more detail. This is all being incorporated into our technical guidance manual, the sampling theory and multi-increment sampling sections, originally dated 2009. We're hoping to post updates, including all our experience in the last few years by the end of the year. Well, why do we do this project? I love the movie, The Matrix. I was rewatching it a few years ago, and here's a great quote. I'll let you read it. But we've always known for 20 years since I got started in this business that something was off with the way we're doing discrete sampling. It's highly inefficient in the field, which we'll talk about in a minute. And, we made the transition, like I said, to multi-increment sampling 10 years ago. We still use discrete sample data, either existing or tight grids of data, say with a portable XRF or something, to, in a qualitative sense, to help us identify spilled areas and designate decision units. And you've heard us talk about that before. But we really don't understand what the potential pitfalls of this are, because we haven't had a good set of field data to work with. And again, we also need a good set of field data to better explain the problems with discrete samples and what the limitations are if you are using these in the field. So a quick outline, we're going to talk about with a quick problem overview. Then we're going to talk about the field study itself, how we selected the sites, how soil samples were collected. Then we'll go over the results. We're going to talk about intra-sample variability. And this is variability within a single sample, say you send to the lab. If a lab tested a different subsample, then how variable would the results be from the sample you sent to them? Then we'll talk about inter-sample variability. This is just the idea of co-located samples, or variability between very closely located samples around a grid point. And then we'll talk about estimated total variability around any given grid point at the sites that we looked at. And then we'll briefly talk about the origin of discrete soil sampling, how did this get started in the first place, and then we'll summarize the study and talk about initial implications. So what's wrong with my discrete samples? Anyone who's been working in this field for a couple of years is very familiar with these problems. It's a constant need for remobilization and step-out investigations, where some investigations we've seen drag on for years as you collect more and more samples and with no really clear endpoint in sight. Also very common to have failed confirmation samples after you excavate an area that you think is contaminated. You collect confirmation samples around the perimeter and you find more contamination, you over-excavate, and you take more samples, and the excavation just keeps growing and growing, again with no clear endpoint in sight. A big issue here in Hawaii is accidental import or export of contaminated soils into sites, especially that are being redeveloped. So even though there was initial discrete sample data for the soil in the first place, but their contamination was later found. So these are common problems I think all of us have dealt with. So something is going on here. Here's an example excavation plan based on discrete sample data. Just to give you an idea, in this case, there are 25 discrete samples were collected within this small area. And in reality, no one would collect that many samples in this small of an area just due to cost. And it's a very common question, how many discrete samples should I collect at a site? Well, in reality, a lot of times that's based on budget. It's not really based on science, which would be difficult to do anyway. So you take your budget allocated to laboratory analysis, divide that by the cost of analysis per sample, and that's how many samples you can collect at a site. In reality, that's the way it works a lot of time. So you collect your samples, and then you find these apparently isolated hot spots and cold spots within a site. That's an initial flag that something is going on here. And then based on your initial data, you excavate the contaminated soil, collect confirmation samples, and like we show in here, it's very common to have multiple failed confirmation samples. So this would require additional excavation, additional resampling, again with no clear endpoint in sight. And this can add significant time and cost to a project. And this is really a major financial and legal burden on people redeveloping sites or attempting to clean up a site. This one flag that immediately should pop up is that we've been comparing published soil screening levels to discrete samples, when in reality soil screening levels are intended for comparison to the mean concentration of a contaminant across a targeted area, say an exposure area or something. They were never intended to be compared to individual discrete sample points. So something's going on. So you ever wonder, what if I moved my sample over a few feet from where I collected it? Again, we're talking about discrete samples in the field now. How different would the concentration reported by the laboratory be? And keep that in mind, because that's really the basis of what we're trying to do in this study. But what if the laboratory tested a different subsample of the soil? If they open the jar and scoop out a gram or a few grams of soil to test the contaminants are concerned, how different would it be if they tested a different pinch of soil from that jar? That's something to keep in mind too. For metals, laboratories typically test around 1 gram of soil, just a pinch. For VOCs, about 5 grams, enough to fill a bottle cap. PCBs, pesticides, it's dioxins, your heavier contamination, 10 to 30 grams, or say a spoonful. So ultimately, that's what your discrete sample data represent that you get back from the lab, really is somewhere between a pinch and a spoonful of soil. There's an idea of homogenizing samples in the lab, where in reality, that never happens in the laboratory. And try doing that in a jar, as one chemist told me. And there's no real process to do that. If anything, you make it worse by letting the fines settle out to the bottom. Well, we wondered about this too. What if we moved our sample point over a little bit? How different would it be? So we set up this field study, and we selected 3 different sites in Hawaii with different types of contamination. The first study site on the Big Island, we knew to be contaminated with arsenic. It's from wastewater discharges or maybe pesticide use in the past. And we already had data for this site. We knew that concentrations of arsenic from one point to another, they're variable, but not that much. At the second site we looked at, our study site B, we knew to be the soil was contaminated with lead from an incinerator ash mixed with fill material. And we knew from data at this site, discrete sample data we had, that there was a little bit more variability between samples. But again, we didn't have a good idea of what the magnitude was. Study site C was used to be a former radio station. The soil was contaminated with waste transformer oil, electrical equipment oil that was just dumped outside the radio station. And again, we knew from existing discrete sample data at this site that it was highly heterogeneous compared to the other sites. But again, we didn't have a good idea of the magnitude of variability, just how far off discrete samples could be. So those are our 3 study sites. Each one of these study sites, we picked an area between 1,500 and 13,000 square feet. We designated 24 grid points. And at each one of the grid points, we collected discrete samples from the upper 3 to 6 inches of soil. We also collected multi-increment triplicate samples from the same study area at each point. We're not really going to talk about those in this presentation. We might mention it in the next one. Now, at each one of the grid points at each site, we did 2 things. The first thing we wanted to look at was what we're calling intra-sample variability, or the variability within a single sample that you sent to the laboratory. To do this, we collected minimally disturbed 200 to 300 gram samples from the center of the grid point. For the metals, we'd put them in a plastic container, and then we had them analyzed with a portable XRF in a laboratory here, where the laboratory tested 10 random points within the sample. We looked at the variability between the results. For the PCBs, we took a sample from near the center of the grid point, and we split it up into 10 subsamples in 10 small separate jars, and had the laboratory analyze each one of those jars, so mimicking laboratory randomly testing 10 spoonfuls of dirt, essentially, from a single discrete sample. So that was intra-sample variability. The other thing we wanted to look at was inter-sample variability, or variability between co-located samples around each single grid point. In this case, we collected 5 samples around the grid point, 1 in the center, 1 at each corner, and then we had each sample, MIS, multi-increment sample, processed at the laboratory. So the laboratory sieved, or dried, sieved, and then subsampled these samples to prepare a subsample for a testing. So using this approach and the data that we get for the sample, we can fairly confidently assume that the data are representative of the actual sample that we send to it. So the data represent the mean concentration of the contaminant in that sample. Keep that point in mind. So each one of the samples we had tested for a grain size. I want to get an idea of the grain size distribution in the samples. For the metals, the arsenic and the lead site, we had the lab use method 6010B to test. And then for PCBs, those samples the laboratory used method 8082. Now for laboratory processing, again, if you're not familiar with that, under incremental sampling approaches, the samples are air dried and sieved to less than 2 millimeters, spread out into a very thin slab cake, and then 30 to 50 increments or small bits of soil are randomly selected from that sample to prepare a subsample for analysis. So this helps ensure that the data representative of the sample that's submitted, so you get a reliable mean concentration of the contaminant in the sample you sent to the lab. You can test precision of the subsampling approach in the lab with the replicate subsamples. This is rarely, in reality, it's never done for discrete samples. Discrete samples, really, it's just a random small mass of soil tested from the sample that you send to the laboratory. It's not necessarily representative of the sample you send to them. We also collected multi-increment samples at each one of these sites. I'm not going to go over those in detail. We had 50 to 60 increment triplicate samples in a random, systematic random grid. And again, they were processed and tested at the laboratory. We'll mention those in the next webinar. Let's look at what we found now. Here's study site A, the arsenic site. This is located on a pond or an estuary. Hilo Bay is actually part of the ocean. On one side, this estuary was a former sugar mill that used arsenic as weed killers back in the 1910s and 1920s. The other side of the back part of the estuary was a former canik factory. And canik is an arsenic-infused wood that was used to fight against termites. So some of the wood was 2 to 3% arsenic. We knew they had been dumping their waste into the pond. There's already data with arsenic contamination in the pond. The soil type there was very fine grain soil, mostly fine to medium sand and silt and clay. So here's what we found for the intra-sample variability. So again, each one of these grid points that we had the laboratory test with the portable XRF, the variability of arsenic within each single sample at a grid point. This is grid point 15, just to give you an idea. The lowest concentration they reported for that particular sample was 252 milligrams per kilogram arsenic. The highest was 387 milligrams per kilogram arsenic. This may seem like a pretty high spread just for a field person. The maximum to minimum ratio of 1.5, so the maximum concentration is 50% higher than the minimum concentration. Well, the standard deviation is only around 14%, so really that's a fairly tight spread. And one point I bring out here is the arsenic in the soil is tightly bound to iron in the soil and a very low bioavailability, so believe it or not, it doesn't really pose a significant direct exposure risk. That was our intrasample variability data. Here's what all the sample data looked at for that site. Variability within samples. Now, on average, the ratio of the maximum to minimum concentration of arsenic at each grid point was around 1.5, about the same as the example that I just showed you, and a fairly low relative percent difference. So you can see in the graph here, the grid points at the bottom, we do have a few outliers, if you want to call them that, where the ratio of the maximum to the minimum concentration was a lot higher. So the maximum concentration was more than 2 times the minimum concentration reported in that same sample. That gives you some idea of variability. This is probably due to the presence of iron hydroxides in some of the samples, and the iron really absorbs the arsenic. So if you got a small nugget of this iron hydroxide in the aliquot tested by the laboratory or under an XRF, then you'd expect to see a lot more variability. Here's the relative standard deviation between the samples. Is still fairly low, 12%. This is the deviation between the 10 points tested with any individual sample. So again, fairly tight data for any individual sample. You do get a few outliers where your relative standard deviation is starting to approach 30% or the magic 35%. So you're getting a lot of variability within some single samples. And again, that's probably due to the presence of small iron hydroxide nuggets infused with arsenic in the sample. So that was the intra-sample variability. How about the variability between co-located samples around a grid point? Well, it was very similar to that. Here's the same grid point, the 5 samples we tested around the grid point. The lowest concentration of arsenic identified in the 5 samples was 230 milligrams per kilogram. The highest concentration was 290 milligrams per kilogram. That's actually fairly tight, not that high of variability. Now this was tested with method 6010B. So you can't directly compare it to the XRF. The XRF analyzed samples typically reported about 30% higher arsenic in the soil than the lab method 6010B. This was due to incomplete extraction of arsenic from the samples at the laboratory. So if we adjust the concentrations of arsenic reported in the process samples upwards by 30%, in this case, the average concentration around this grid point was 333. So very similar to the average concentration we had just for the one sample tested in the middle. So here's just a summary of the ratios of the maximum to minimum for the intra-sample data or the co-located samples. Again, fairly low. The average maximum min ratio 1.4. So relative percent difference only about 40% higher for the max concentrations. You see a few outliers where the variability around a single grid point approached 2 times. So that would mean that if you tested the sample in one point of the grid, at a grid point, it might be 100 ppm. Well, around that grid point, you might see concentrations up to 200 ppm arsenic in the soil. These are the process samples. The relative standard deviation, we only had 5 points, but around each grid point, still fairly low, 14%. So this, on average, there's not that much variability around a single grid point, although we did see higher variability around some grid points. Again, that's probably due to the presence of iron hydroxide nuggets infused with arsenic in the soil around that particular grid point that we happen to catch. Well, that's interesting, but it doesn't answer the full question. We want to know what the total discrete variability is around any individual grid point. So if I move my sample over a foot, how different could my answer be? And that's going to be a combination of the intra and inter-sample variability. So here we are back at grid point 15 for the arsenic site. And to do this, we can adjust the process sample means with respect to the mean relative percent differences that for the variability we saw within that one sample that we tested 10 times. So in this case, at grid point 15, for the sample we tested 10 times, the minimum concentration was 23% below the mean. The maximum concentration in that sample was 18% above the mean. So if we use this and adjust the concentrations for our process samples around each of the grid points, we get a better idea of what the spread of the discrete sample concentrations would be. In this case, at sample A, the mean concentration reported by lab for that process sample, 250 ppm. So using the relative percent differences from the inter-sample variability, we can say the estimated minimum concentration would be 23% lower than that, 193 milligrams per kilogram. Estimated maximum concentration, 18% higher than what was reported by lab for that sample, to 285 milligrams per kilogram. So we get a more realistic idea of what the variability is. We can apply this to the other grid point samples. In this particular grid point, sample C had the lowest concentration reported of arsenic. Again, these were the process samples, 230 milligrams per kilogram. Again, applying that same difference for maximum, minimum relative percent difference, we just estimate that the minimum concentration we might find in that particular sample, if we just tested 1 gram aliquots, would be 177 milligrams per kilogram, or 23% lower. And the highest concentration of arsenic we saw around this grid point, sample E, 290 milligrams per kilogram. So if we tested individual 1 gram aliquots from that particular sample, we'd estimate the maximum concentration we find to be 18% higher, or 342 milligrams per kilogram. This is just to give a general idea of the variability, the wider spread variability we might see around any particular grid point. In particular, for grid point 15, we'd expect to see arsenic variability between 177 and 342 milligrams per kilogram for any specific discrete sample randomly collected. We only tested a small amount of the soil around a grid point. If we tested more soil, we'd see more variability in this. That gives us an idea, and we can finally start to put a handle on what the magnitude of variability might be. So in this case, about twofold. And that's about it. We see about an average of twofold variability around any given grid point at the arsenic study site. This is just box plots of the grid points versus the estimated variability of arsenic concentrations around each grid point. Again, the average is about, for the maximum to minimum concentration, about 2 times. So again, at any point in this site, if you collected a discrete sample and you came back, the lab reported 100 milligrams per kilogram arsenic, then we could say, well, it could be up to 200 ppm, or 2 times, or it could be half that of 50 ppm. And again, you can see the highest variability we estimated at a site here. The grid point 4 ranged between about 220 or so ppm arsenic up to about 750 ppm arsenic. That's the variability we estimate you'd see around that grid point if we tested a lot of discrete samples. That's in general, this site, if you want to think of it in gumballs, it's fairly similar. If you test it around a single grid point, you get a little bit of variability around the grid point, but not that much if you consider 2 times, or plus or minus 50%, not a big deal. Let's look at the lead site. This is a former municipal incinerator. Again, it's at the north end of Pearl Harbor. The soil type of this site is, this is fill material. So it's a silty sand, or a sand with gravel in it. After we sieved the soil down to less than 2 millimeter fraction, it's still dominated by fine sand and medium sand, with just a small amount of silt and clay. So it's a much coarser soil type. Here's what we saw with the intra-sample variability. Again, so at each grid point, we tested the sample 10 times. This is grid point 18 at the lead site. So testing that one sample with the XRF, the lowest concentration of lead reported was 123 milligrams per kilogram. The highest concentration of lead in that same sample, 504 milligrams per kilogram. So we're seeing a lot more variability within the samples here. In this case, the maximum to minimum concentration about 4-fold. Relative percent difference a lot higher, 310%. Relative standard deviation, obviously a lot higher, also 35%. The average concentration of lead, just within that sample, if you average all 10 subsamples, is 293 milligrams per kilogram. That was pretty typical of the site in general. Is a graph, again, of the grid points and the ratio of the maximum minimum concentration for each, the single samples tested around each grid point. Again, the average maximum minimum ratio is about 4 times, 4-fold, so the relative percent difference is a little over 300%. But you can still see here at some of the grid points, like grid point 2, within that single sample, we saw over an order of magnitude variability between lead concentrations. So imagine that if you send a sample to the laboratory and they test it once and they find 10 ppm, they test it again, they find 100 ppm. Probably this was due to the presence of pure ash nuggets within that particular soil sample. And that 1 gram that was tested by the XRF happened to pick up a lot more of the ash in that particular sample, so you got a higher lead concentration. In general, though, the ratio, the variability within samples was pretty consistent across the site. And I liken this to grabbing a handful of a salad. So any particular salad, you see a lot of variability in it. But from place to place, grid point to grid point across your salad, you're going to see pretty much the same thing. Here's the relative standard deviation we saw within individual samples tested, around 40%. Again, it's definitely getting to a level of concern as far as estimating mean just from the data. It just gives you an idea of how much variability we're seeing. Let's look at the co-located samples now, the inter-sample variability for the lead site. Here's a typical grid point 18. You see the lowest concentration of lead in the samples collected around this grid point was 200 milligrams per kilogram. Highest concentration was 620 milligrams per kilogram, just a foot away. Now, one thing to point out is this variability we're seeing around grid points is completely random. This doesn't mean that as you go down to the bottom right part of this grid point, we have 620 milligrams per kilogram, that lead concentration soil is increasing in that direction. You can go another foot out and get 200 again, or 50. So this variability we're seeing is completely random within the co-located samples. So again, you see the maximum minimum concentration around the grid points. On average, the maximum concentration was 3 times higher than the minimum concentration. So RPD around 200%. Relative standard deviation now, again, we're getting higher, 45%. The average concentration of lead, in this case for these 5 samples, 356 milligrams per kilogram. And it was similar to the first sample that was tested. One thing we did note here is the XRF was slightly underreporting concentration of lead compared to method that should be 6010B, probably due to moisture in the sample. So here's the variability summary for inter-sample data at study site B. Again, the co-located samples. You can see it's still fairly consistent. Again, it's like handfuls of salad. They're common from place to place, even though you see a lot of variability within the sample. So the average maximum minimum concentration a little bit lower than we saw in the individual samples, 2.3, and the relative percent difference a little over 100%. Again, you see these spikes where around some of the grid points we saw up to 7 times a difference in the maximum minimum concentration of lead in co-located samples around a grid point. This is probably because that one particular sample had more ash in it than the other samples did. Again, it's completely random. The relative standard deviation, again, we're pushing 40%. The variability around with co-located samples around grid points. Again, we're seeing a lot more variability at the lead site than we did the arsenic site. Here's a summary that for the lead site of the estimated total discrete sample variability. So again, around each one of the grid points, based on the data we have, how much do we think the variability or the discrete samples concentrations could vary around any individual grid point. So you can see here that the average is around a little bit under order of magnitude, 7.5 times the maximum to minimum concentration. So that's starting to get fairly significant. Interesting thing here, and the red lines are a little bit off, but the screening level used for lead in soil in Hawaii is 200 milligrams per kilogram, and at 23 of the 24 grid points, then we're estimating you could find a discrete sample around that grid point that's both below and above our screening level of 200 milligrams per kilogram. If you use EPA screening level of 400 milligrams per kilogram, and again, around each one of those grid points, 20 out of 24, we estimate you could find a concentration of lead in soil either above or below 400 milligrams per kilogram. So really, these are, I call these opposing gumballs. You can get a red one or you can get a green one. It's just completely random at each grid point what you happen to get. So think about that as far as trying to do a discrete sample investigation across this site. You really be chasing your tail and trying to use discrete samples. This is just a fraction of intra-sample data above and below 200 milligrams per kilogram. So just the XRF data for each individual sample. And you can see this, that most of the samples at grid points across the site, you could find discrete sample. You can find concentrations of lead above and below 200 ppm. This is why your confirmation samples fail, why you end up in such a mess in the field. Let's look at the last site. This was PCB site. Interesting thing with this site is that we knew it was contaminated with PCBs. There were 3 different soil types here. There's fill material on one part of the site that was brought in, and we already knew the fill material was especially contaminated with PCBs. On the other side of the study site was native soil, which we already knew also it was less contaminated, although it was still contaminated, and then a mixed zone in the middle. So at this site, looking at the native soil first, again, we're back in that fine grained soil. And the reason we did soil analysis, there was some idea that we'd see less variability in fine grained soils versus coarse grained soils and such. In the end, we didn't really, but that data is in our report. So the native soil at this site was a blackish brownish clay, really a clay, fine grained silty sand, sandy silt. The fill material at the site, if you're familiar with Hawaii soils, it was a mix of the volcanic red soils and red cinder, or volcanic cinder. So it's much coarser, gravelly. After you sieved out it just looked at less than 2 millimeter fraction. It was still dominated by silt and clay, but with a substantial portion of sand, actually dominated by sand, but a large portion of silt and clay in the sample also. It's very mixed. Here's what we found at the PCB site. This is a typical grid point. This is the sample. So at this grid point 24, we collected a single sample, split it up into 10 jars, and had the laboratory analyze each jar. And the concentration of PCBs reported by the laboratory ranged from 810 milligrams per kilogram to 5,700 milligrams per kilogram. So just in this sample, we saw a 7-fold difference between the minimum and maximum concentration of PCBs reported in the sample. And you see your relative standard deviation now, you're up to 62%. So it's telling you you've got a lot of variability. Now keep this point in mind, the average concentration of PCBs in that sample was 2,400 milligrams per kilogram. So let's look at the 5 samples tested around that same grid point. Oh, actually, we'll do that in a minute. Quick to summarize this, the variability around each one of the grid points, intra-sample variability, average was over an order of magnitude. So you'd see over an order of magnitude variability in PCB concentrations within single samples collected at each one of the grid points. And you can see it's highly variable, even across the site. Some of the sites we saw over 2 orders of magnitude difference in the concentration of PCBs reported for a single sample when we tested 10 different subsamples. And this is probably due to the presence of PCB nuggets. So something's going on. We'll look at that in a little more detail in a few minutes. Something really odd is going on with the PCBs at this site. Now, the relative standard deviation, again, we saw in the intra-sample data, we're up to 70% here now. So there's a lot of variability within a single sample that was sent to the laboratory to test for PCBs. To keep that in mind when you're testing for PCBs in soil. Let's look at the inter-sample variability. This is the variability between co-located samples around individual grid points. Here's another typical grid point. It's the same one we looked at before, grid point 24. Still pretty high. The minimum concentration we saw in the sample collected at the grid point, 4.9 milligrams per kilogram. Remember, these are processed. And the highest concentration we saw just a foot or 2 away was 91 milligrams per kilogram. So on average at this site, the maximum to minimum concentration PCBs in these co-located samples was 19. Your RSD is 151%. So it's a lot of variability. And again, this is completely random. On the other side, this 91 milligrams per kilogram PCBs, you might find 1, or you might find 1,000. It's completely random. This that same sample we tested from this exact same grid point. We split it into 10 different jars and had the laboratory test each subsample. Remember, the average of that sample was 2,400 milligrams per kilogram. So that's a lot of variability. The lowest concentration of PCBs around this grid point, 4.9, the highest sample collected maybe a foot away, if that far, 2,400 milligrams per kilogram. So there's a hot spot. You hear a lot of the incremental sampling people saying there's no such thing as a hot spot. Well, here's a hot spot. This is a true one, and it is a spot. It's only a few inches across. So looking at a summary then of the inter-sample data variability, the co-located samples, on average, around any grid point at the PCB site, we saw an average variability of between the minimum and maximum concentration, about the order of magnitude for the different grid points. Again, some of the grid points, we saw a lot more variability between the maximum and minimum concentration of co-located samples up to 40-fold variability. And the relative standard deviation, again, coincidentally 72% again, is still really high. So we're seeing a lot of variability between co-located samples around individual grid points. So this side, here's a summary of the estimated total discrete variability. I had to put this on log scale. There was so much variability around individual grid points at the site. The median maximum to minimum concentration of PCBs around any individual grid point was almost 40-fold. And at one particular grid point, the one we looked at, it was almost 1,000-fold. So that's obviously huge. And again, at this site, there was our office used a residential screening level of 1.1 milligrams per kilogram for PCBs in soil residential. 8 of the 24 grid points, you could find discrete samples around those grid points, both above and below our screening level. And looking at TSCA cutoff for disposal landfills of 50 ppm, and 12 out of the 24 grid points, if you test around those grid points, you could find a discrete sample with the PCB concentrations both below and above 50 ppm. And this is, we only tested 5 samples at each grid point. If we tested more, we see more variability, obviously. So there's a lot of variability at the PCBs in soil. We've seen this at other sites. If you had to compare this to a jar of gumballs, then it's a total mix. It's a really random number that you get from the laboratory when you get a concentration of PCBs from a discrete sample at a grid point, at least at this particular site. So why is this happening? And we've already talked about this in some other webinars. But one thing we looked at, we started looking at the soil under a microscope. And we suspected there were nuggets of PCBs. We never really heard of it before. But under a microscope, you could see these small, dark clumps of soil, just a few millimeters across. And if you pushed on them, they were easily broken, so they weren't lithic fragments. There was something going off the soil. And if you zoomed in even closer in the upper left-hand corner, you see what looks almost like an egg. And this is what we think is a PCB-infused nugget of oil that sank into the soil. So some local chemist who likes to cook showed me how to make these. If you take olive oil and drop it on dry flour, then the oil immediately will bead up into small beads, and then they'll slowly sink into the soil. And take a look at the droplet here that sunk into the soil. You see that outer rim, a thin rim where you have more flour in the outside part of the droplet. And quick jump back to the previous slide. Look at the small nuggets, what we think are PCB-infused tarball nuggets in the soil. You see that thin outer rim of soil around that nugget also. That was really interesting. Now you could let the oil and flour sit for a few minutes, and you can actually sieve out these olive oil-infused nuggets in the flour. This is what's happening at the PCB site. We're almost positive. If you happen to get one of these little infused nuggets in the subsample tested by the lab, you're going to get really high concentrations of olive oil with PCBs. If you don't, then you'll get lower concentrations. This is what's causing the variability we see at the PCB site. Now, this gets back to the myth of maximum contaminant concentration in soil. That's so much of a culture of discrete samples where you're trying to find the maximum concentration of a contaminant in the soil. Well, if you looked at this same sample here, you get 3 different concentrations from the sample we sent to the lab. If they tested the entire lab down the bottom sample, you get a pretty low concentration of PCBs. If the laboratory could actually analyze one of these single nuggets of PCB-infused dirt, then they get a much higher concentration. Now, if you could zoom into that nugget and actually test just a matrix, the leftover PCB oil, then you could, in theory, find a concentration of PCBs up to 100%. So it's really a key point. You hear this in ITRC's ISM webinars and in our guidance that concentration varies with the mass or the volume of soil tested. That's something critical to know, understand, and that's why it's important to designate your decision unit for your targeted volume and area of soil tested where you want a mean concentration. It's going to vary depending on how much soil you test. If someone wants to know the maximum concentration of a contaminant in soil, it's easy. You don't need to go out and search a lot. Collecting lots of discrete samples, it's either 1%, 0% if it's absent, or if it's present at some scale, it's 100%. If you could zoom in on a particular particle of that contaminant, analyze it, it's going to be 100%. And so it's really a meaningless approach to try to take it aside, or a meaningless search, trying to find a maximum concentration. The objective is always to estimate the mean concentration of a contaminant in both the sample sent to the lab and also in a designated area or volume of soil at the site. Here's a summary of the data we found in the estimated median total discrete sample variability for the study sites. So at study site A, the variability of arsenic concentrations around any given grid point, it would vary, we'd estimate, by a factor of 2. So again, at a study site A, if laboratory reported a concentration of arsenic of 100 ppm in a discrete sample, then we'd say, well, it could be 200 or it could be 50. At study site B, the average variability around individual grid points was almost an order of magnitude 7.5 times X. So again, if the laboratory reported 100 ppm in a discrete sample for a grid point, it could be as high as 750 ppm in other discrete samples around that grid point, or it could be much lower than that, with a little 10 or 15 ppm around the same grid point. That's the kind of variability you could potentially see at a site. PCB sites, again, are all over the place. You can see, on average, we saw 39-fold variability between, or estimate between discrete samples around individual grid points at the PCB site. And again, some of those grid points, the variability is over 1,000-fold. If we tested more samples, we'd see more variability. And here's just the same thing expressed in relative percent difference. And here's just looking at the relative standard deviation we estimated for discrete samples around individual grid points. Pretty low at the arsenic site, like we anticipate in the future when we first started the project, but now we can start to put a number on it. A lot higher at the incinerator site where lead contaminated ash is mixed with fill material. Again, think of this as like a big salad. You see a lot of variability within individual samples, but from point to point, it's similar variability. And then the PCB site, relative standard deviation is much higher, over 100%. The PCB site I liken to, instead of a single salad, it's like a salad bar. So any discrete sample is just a different part of a salad bar that can be hugely different. So that's why confirmation samples are so unpredictable at sites, and why it's so difficult and inefficient using discrete samples to investigate even the extent of contamination at the site. It's due to the small scale random variability of contaminant concentrations over a few inches or a few feet. And again, the concentration reported for any discrete sample is largely random within a range for that particular site, and you can't fix this with statistics. Your statistics can't fix a bad data set. So we're back to our excavation here. If you look in the right-hand corner, there's one of our failed confirmation samples. If you went back and tested a sample from this corner, and it's random what it could be. It could be above your screening level or below your screening level. In the end, that's not the point, because your screening levels are never meant to apply to tiny, really random masses of soil at a site. And you can't fix this problem by collecting more and more discrete samples. You just dig yourself literally into a deeper and deeper hole. So that's the root of the problem. I know we talked a lot about sampling theory and such, and we'll talk about that more in next webinar, not a whole lot, because we're really focusing on the problem here. But really it comes down to discrete samples are just too small. They're too small to capture the inherent random distributional heterogeneity of contaminants in soil at a site, where you're just testing pinches or spoonfuls of soil. And even processing discrete samples, which we require under our guidance, but that still doesn't address random variability around the grid points. There's still a lot of uncertainty, even if we use discrete samples to set up a grid, say in the field, and estimate or try to identify where specific spill areas are for more intense characterization with multi-increment samples. We still can't completely trust our discrete samples, because we still see a lot of variability around individual grid points. Here's something that's one of the few artists I remember from my undergraduate days taking art appreciation classes was Jackson Pollock, who just liked to splatter paint on canvases. That's what I think a lot of the contamination in soil would look like if you could actually see it, which of course we can't. So on the left, here's one of his paintings, and that cutout box, that little red dot, is actually the size of a discrete sample. It's about the size of this foot. You might collect at this site and send to a lab. Or just imagine if you move that discrete sample over a few inches in either direction, you could get much higher or lower concentrations of this dark colored material. On the right is a truck that milk spilled from. Imagine this if it was gasoline or solvents or something you couldn't really see in the soil anymore. And so just collecting a small, random discrete samples within the milk spill here, you might find the core of it. And that's what we find a lot with, we go back and look at old discrete sample investigations. You'll find more often than not the core of the contamination, but you'll pretty quickly miss contamination when it becomes more heterogeneous in the field. And that's one of the myths, I think, of discrete samples, is they work best in heterogeneous environments. It's actually entirely the opposite. Discrete samples really only work well in relatively low heterogeneity or homogeneous, we use that term, releases. So how did all this happen? That's one thing I'm curious about. Why, if there's so much variability, why are we doing this? Why we've been doing it for 30 years? So I went back and looked at some of the original guidance, and we focused a lot on PCBs here. Here's some quotes from EPA's 1985 guidance, verification of PCB spill cleanups. This is the basis of TSCA regulations and guidance, where they establish grid sampling methods and such. So here's one quote: the implicit assumption that contamination is likely to be uniformly present anywhere within the sampling area is reasonable. The PCB level is assumed to be uniform within a contamination zone or spill area, as we would call them now, and zero outside of it. So these are critical assumptions. And why are they saying this? Because that's the case that you would get with transformer oil. If you tested oil within a transformer, then you can assume fairly reasonably that the concentration of PCBs is consistent within that transformer. So if you dump this on the ground, the thought was at the time of the concentration in soil should also be similar. Here's a quote from EPA's 1989 guidance, methods for evaluating the attainment of cleanup standards. When there is little distance between points, it is expected that there will be little variability between points. Well, now we know that's not really true. So there was a lot of untested assumptions in the early guidance that we're still adhering to. Here's another quote, EPA's 1987 guidance, data quality objectives for remedial response activities. To apply this discrete sampling method, the following assumptions are required. The shape and size of the contaminated zone, or spill area as we call them, must be known at least approximately. So this is what we're doing now when we go out in the field and designate spill area decision units. Any sample located within the contaminated zone will identify the contamination. That's a key assumption using discrete samples and grids. But at the time too, they concluded these assumptions are not severe and should be met in practice. So what they're saying, if you go back and look at the guidance, is that a single discrete sample should be adequate to identify a spill area. That's really the basis of grid sample spacing. In this case, they were just using what's available again. Their early soil sampling guidance was based on experience with industrial waste streams or testing oil from transformers and such. So you expect it very, very consistent. If you have a liquid waste coming out of an industrial facility, say a textile mill, it's not really going to vary that much from day to day unless they change the operations inside. So it doesn't really matter the mass that you test or when you test it, it's going to be the same. One thing with the soil is the reliability of discrete sampling methods for soil was never tested in the field, which I was surprised. There's lots of hints over the years where people are seeing problems, but no one's really tested it in detail except for the Army Corps now with munition sites. But for things like PCBs, lead, and arsenic, not really. Also, the implications of sampling theory in the 80s and random small-scale heterogeneity for contaminated soil wasn't really fully appreciated, although the mining companies, mineral exploration, agriculture quickly jumped on sampling theory and incremental samplings, and they've been using that for decades. There's also a lot of confusion if you go back and read the early guidance on the methods to estimate health risk. And there's confusion over how you use screening levels that are being published at the time or just started being published in the early 90s. Whether the screening levels apply to every testable mass of soil, 1 to 30 grams, or which is wrong, or where they apply to the mean overexposure area. So there's a big divergence between the risk assessment people and the field people, where the risk assessment people knew that you can trust an individual sample to estimate mean concentrations and clear areas of contamination, but they were sort of sidelined. So here's, if you had to summarize this in one slide, and here's a slide I put together just to explain why soil is different from industrial waste streams and why discrete sampling methods don't work for soil like they do for waste streams. And what we assumed in the 1980s basically is that contaminated soil is like a bowl of Cheerios. You can grab any single piece, and it's going to be the same as the ones around it. And doesn't really matter what the mass of Cheerios or soil you test are or where you collect the sample, you'll get pretty much the same number. That's why now the size of the sample collected in the field is completely controlled by the laboratory. They really know the science behind sampling in the field in terms of discrete sampling. What we know now, after 30 years, is in reality contaminated soil is more like a bowl of Fruit Loops, where your concentration of a contaminant in even a given soil sample can vary widely from aliquot or subsample to subsample or co-located sample to co-located sample. The only way you can overcome this in the field is to collect a really large sample and designate the area that sample applies to, which is the core of sampling theory. And I was always wondering too, when did this really diverge? Because like I said, the mining companies, agricultural companies have been using incremental sampling methods for decades now, but in environmental, we stuck with the discrete sampling. So when was that missed opportunity? If you had to go back and put a date on it, I would put it in 1985 with this manual. It's the field manual for grid sampling of PCB spill sites to verify cleanup. This was something published by EPA at a time when they were first publishing their PCB regulations, and there were thousands of sites across the U.S. that suddenly needed soil sampling. So they came up with the discrete sampling grid methods. In 1985, in 86, they went out and did a field validation of this exact guidance. But the only thing they looked at was the ease of laying out the grid. No sample collection was carried out to evaluate the assumption of that uniformity of contaminants in soil. My guess is because they didn't have the budget. I guarantee when they were out there laying out the grid, they were wondering, gee, what if I tested my sample over a foot this way or a foot that way? How much different would it be? But they never did. But they were aware that, very clear if you read the guidance, they're very aware that new information may arise in the future and new approaches may come out. Here's a quote at the bottom from the same 1985 guidance. The future changes in EPA policy may invalidate some of the discussions in this guidance. That's really what we're working on now, is between our field data and other discussions. It's really invalidating the use of discrete samples at PCB sites. Not that they're necessarily wrong, but you can get a cleanup done, but they're highly inefficient. So just start thinking about the implications now of this, the representative of your lab data for samples that you get back from the lab. It's not really representative of the sample you got. You can't trust it. The comparison of individual discrete samples to screening levels for site investigations, think of the reliability of that and how much variability you might see even between co-located samples. And the estimated extent of contamination tied into this, the ISO concentration maps, think about those. We'll look at those a lot in the next webinar. What are these isolated hotspots that you see on these maps? Are they real or are they just artifacts of heterogeneity? You can take a guess on that. And the use of discrete samples and risk assessments. How do you know that 20 sample set is actually representative of site conditions or not? So we'll talk about that some. And also the use of discrete samples in remedial investigations. That's the next part here on October 21st, two weeks from now. We'll look at part 2 of the study, which is really the fun part. The data, that was nice. It was fun to do the field work. We'll probably never do it again. Part 2, we especially look at the implications for the use of discrete samples in environmental investigations. We'll look at random patterns that we can generate now at each one of these sites because we have all this data for individual grid points. They're completely artifacts of the heterogeneity. We'll play with a deck of cards and look how we can do the same thing with a deck of cards, just generating random patterns because of variability around the individual points. We'll go to my sister's house in North Carolina, and we'll look at the USGS's map of arsenic concentrations, or background arsenic in the U.S. And according to them, my sister lives on a 2,400 square foot arsenic hotspot in North Carolina that, if you look at the details, it was based on a 1 square meter sample collected in that area. Is that really real? And we'll look at lab testing methods and then the need for processing samples. And again, we'll look at the use of discrete samples for estimating extent of contamination. We'll talk about inliers and outliers. We'll talk about TSCA some. We'll also talk about sampling theory just a little bit. We're going to use a salad to explain sampling theory and incremental sampling. It's really not that complicated in the details. And again, we'll also talk some about risk assessments and 95% UCLs and how reliable they are. So it's just a summary then of the different topics we're going to talk about. At this time, we'll close it out. Another quote from the Matrix in Morpheus. And it is really interesting once you start going down this path, thinking about reliability, and it's going to make you rethink a lot of things that we've been doing in the past. It definitely has with us, and we're still rethinking it. So this time, Jordan, I'll open it up for questions.
All right, hey, thanks Roger for that. And if you're ready for questions, we can go ahead and start going through that. And also for all the viewers, once again, thank you for joining. And if you do have questions, please submit them through the question and answer that you can see from your webinar menu. We've got one at this time. So Roger, I'm gonna go ahead and read it. And when you're ready, just feel free to answer it. The question is, do you have a feel for the granularity of an analyte's distribution? Meaning if specifying a co-location radius and vary that co-location radius, how does the variance change?
Not really. We set it, say, a 3-foot radius, a 2-foot radius around individual grid points. So yeah, for the variability, we don't really. It more depends on the release scenario. That's something we're going to discuss in the updates to our guidance. If you have a release scenario, something like water-based pesticide, we'd expect the variability to be much lower. But you can get tricked because of something like arsenic that'll concentrate around iron hydroxide nuggets in the soil. You still see more variability than you might expect otherwise. So in our updated guidance, we do discuss that to some degree. It's more of a guide on how many increments you need to collect at a site in order to characterize it reliably. So as the variability increases, like to the lead site, instead of 30 increments, we would recommend a minimum of 50 increments for any decision within that site before you can start getting reliable mean for a targeted area. The PCB site is a mess. And for that one, we're recommending that you increase the number of increments for multi-increment samples to a minimum of 75. And that's really what you need before you start getting consistent representative data for a targeted area. So for discrete samples around an individual grid point, it's hard to say. And again, there's no way to fix the discrete sampling problem. There's one thing, it's a common statement I hear is, well, this is it's another tool in the toolbox. And that's actually not the point. This is, what we're talking about here is an entirely new toolbox and a much more efficient toolbox, where maybe discrete samples are a tool in this toolbox just for qualitative screening, but we're not adding a tool to the toolbox. We're coming up with an entirely new method.
Okay, thanks, Roger. That looks like all the questions we have for now, but if anyone has more questions, we'll keep things open for another minute or so, and just feel free to submit them.
And well, I expect to get a lot more questions really in the part 2 of the webinar is when we start looking at the implications of the variability we see. And so random small scale variability with discrete samples, implications for using them in the field and for evaluating data that we already have. Because we don't just ignore existing discrete sample data at sites. We'll use it to help set up investigations, more detailed decision and then multi-increment sample investigations. But this study we did gives us a much better idea of how reliable those data are.
Yeah. Another question just came through, and it has to pertain to the depth at which the samples in the case study were collected. The question being, why did you decide to sample between 3 and 6 inches?
And actually, so it was the surface down to 3 inches or down to 6 inches. Each one of these sites, well, let's say at the arsenic and the PCB site, we knew that the release was at the surface, the contamination was. And we already knew there was contamination there. At the lead contaminated site with the incinerator fill, some of that fill material goes down 10 feet. But again, we knew we had contamination just at the surface. And the main objective of this investigation it wasn't to map out contamination at these sites. It was just to look at variability around individual grid points and how that may differ between different contaminant release scenarios.
Okay, thanks, Roger. Another question that popped up, did you do any processing in the field, or did the lab do all the processing? And what does that add to the cost?
Yeah, so all these, in the field for the intra-sample variability, where we looked at variability within individual samples, then we intentionally didn't do any processing at all. Those samples were collected as undisturbed as possible. The process samples, which we had 5 at each grid point, so 120 at each one, to look at variability between the co-located sample, we had all those samples processed. That's between $75 and $150 per sample. So that's the one problem with discrete sampling. Just as far as getting a data back from the lab that represents your sample, they really have to process it. You have to collect enough soil so they can process it and subsample it. But you can add on $100 to your analytical cost. So even though it's in our guidance, you have to do that if you want to make a call on discrete samples, and no one really does it. It runs up the cost too much. But multi-increment samples, you're collecting far fewer, so it's economically practical and necessary to process them in the lab. So this whole project, somebody's probably wondering, how much did you spend on this with my federal tax dollars? This whole project, we spent about $75,000 to throw it out there. And at the PCB site, for example, we collected over 300 discrete samples in 5 hours, and then we had 120 of them processed at the lab. Our hope is it's already saving a lot of money. The state is at new PCB sites and other sites where we're moving toward just using incremental samples.
Okay, one more question. Given what you have discovered about non-volatiles and heterogeneous soils, what good is soil sampling for VOCs?
Yeah, and well, actually we did a study several years ago where we did something similar to this. We looked at variability of VOC concentrations in soil at a TC study, and that's posted to our webpage. And you see the same variability with VOCs in soil. Discrete samples are only testing 5 grams, about the size end of your thumb. You move that sample over a few feet or a few inches, you can get a completely different number. So yeah, soil sampling for VOCs, especially discrete samples, same thing. It'd probably be like the lead site, not that reliable. It gives you presence or absence, something like that, more of a qualitative sense. And really for VOCs, if you have VOC contamination, one of the main concerns is going to be vapor intrusion. So the next step, if you think you have contamination at all, is to go get soil gas samples.
Okay. And I guess we have time for another question or two, but one more here we have is, have you had any experience with assessing more mobile pollutants like benzene?
Yeah. Oh, we have so many sites here. We have a good benzene story where there are discrete samples were used to estimate the mass of benzene at a benzene contaminated site. It's an old manufactured gas plant site where they actually made benzene. Some of the initial discrete samples, they estimated 5 tons of benzene at this 4-acre site in the subsurface, and they set up a in situ remedial system with SVE and such to treat it. They took out, they basically went bankrupt after 25 tons of benzene. That's how far off the data were.
Oh.
And another company has gone in and done more detailed investigation. They estimate that there's still another 75 tons of benzene or such left at the site. So that's a big issue, and that's really one of the things that's driving the need to move toward incremental samples or multi-increment samples. And we discuss this in our guidance, how to do subsurface samples for VOCs with cores and subsampling and targeted DU intervals and such. But in the end, the reason the agriculture and the mining industries went toward incremental samples is because of money. In the end, discrete samples were inefficient and totally very unreliable. And really that comes into play in environmental work when you start to clean up a site, because that's where the money really starts coming to play and the need to optimize your remediation strategy. It's moving toward a multi-increment samples instead of discretes. So that's the motivation to push for better sampling methods for VOCs and others. It comes in the remediation side.
Okay, 2 questions left. Let's answer those and then finish up. The first one being, how does a lab composite soil samples with VOCs?
Yeah, so for VOCs in the field, you actually, in the composite, we wouldn't use composite. That's one key thing to think about. These multi-increment samples and incremental samples, they're, from a legal regulatory standpoint, they aren't composite samples. Composite samples mean where you're mixing soil from different decision units or different areas, where in multi-increment samples, we're just trying to get a single sample of a soil from one single area, targeted spill area. But for VOCs in the field, here the laboratory will provide you with a jar of methanol, usually a 1-liter jar half filled with methanol. And then for your either say an excavation, you want to know what the concentration of VOCs are, PC in the bottom of an excavation, then when it's still fresh anyway, you'd pick 30 or 50 increments of soil from the bottom of the excavation or 5-gram plugs, and you'd put those in the methanol. Then you send that jar of methanol to the lab, and they test an aliquot of the methanol and give you a concentration based on the mass they detect and the mass of soil put in the methanol. That's discussed in our guidance document. We're expanding the whole section on incremental samples for VOCs. Same thing for cores. You don't just collect a single 5-gram plug, a discrete sample from a targeted depth like 5 feet or 10 feet. You designate specific layers, and then you collect subsamples from those decision unit layers, say a 5-gram plug every 2 inches or something, and put that in methanol. And then have the lab test that so you can get a fairly reliable concentration of VOCs for a targeted layer. But you get away from the idea of targeted depths and trying to extrapolate between depth points where you don't have data.
Okay, last question here. Do you think there is still a role for discrete sampling for screening and initial characterization of sites?
If I would never go into the field again without a portable XRF. if we had the money to carry one along with us. So all these sites, the metal contaminated sites I talked with, when we went out to test the sites just to set up the study area to do investigations, we took a portable XRF with us and did what essentially is discrete sampling in the field, just to help us identify in general where the areas of heavy contamination are. So still, especially with something like that, or say immunoassay kits, then tight grids of discrete samples can be very useful if you can do them financially cheap enough, cost beneficial enough to help identify and focus in on your areas of higher contamination. The only problem is you can't over rely on the concentrations reported or where the exact boundaries are between contaminated and uncontaminated soil. But yeah, they're useful, and that's included in our guidance. And we have some great examples of sites where we were hung up doing decision. It's a multi-increment sample trying to find spilled areas, and someone went in with the portable XRF in the field, and immediately found the hot area. We don't worry about hot spots. We look at hot areas. The portable XRF was an arsenic site. So great to start with, get things going, but it's not something you want to make your final call on.
Okay, thanks, Roger. Great presentation today. The next one will be coming up on October 21st. So everyone has the contact information for Roger. If you have any questions, you can feel free to send those to him. And just keep an eye out for the invitation, which should be out shortly. Once again, thank you for joining us. And yeah.
Yeah, thanks a lot, folks. We'll talk to you in 2 weeks. We go down a trip down the rabbit hole and have some fun with all of our data. Thanks again.